Hey, physics students, welcome back to my basement for our physics class. This is the class of that we would have had Wednesday, April 1st, I guess. Okay, well, here's the Blackboard page. Um, we're going to have all our assignments and tests online for the rest of this semester. So hopefully you've looked around here. Here's Wiley Plus. This is where all our homework's going to be. Most of you are successfully engaged with this now. You should have gotten numerous emails from me. The latest one has the correct registration codes for this. The company originally sent me the registration codes for the wrong platform. But they've straightened that out, and it's pretty nice of them. Some students, a couple of students, actually just called customer support and were able to get on right away. The customer support just gave them a good a working code for free, and if you've noticed, it's about it's $140 as cost. So that's nice of Wiley. Anyway, it's the first time I ever used it. I used similar things. So you click on this, and you should go to the Wiley page. I'm going to go to the student view here. And you have two assignments. Originally, there was a assignment 0 here, but I got rid of it. It doesn't have any physics in it, and it's for the wrong platform as well. So there's some questions that you can't even answer from this. So I got rid of it. People were wasting their time on it. I'll give you all the points. Okay, so anyway, let's look at Chapter 6 homework. It's due, let me see, when's it due? Friday. When's that? Or no, the 5th. The 5th is, looks like the 5th is Sunday. It's due Sunday. So that's not much time, but if you notice, these problems actually were assigned as homework. Most of these, except for these last two, were assigned as homework back on March 9th, the week of March 9th. So if you haven't done anything since March 9th on homework in Chapter 6, you're probably going to have difficulty with this. But if you have been working some of those problems that were assigned, your grade probably will reflect that. So let's see. Let's look at these last two problems. A projectile of mass this is shot straight up with initial speed of this. How high would it go if there were no air resistance? If the projectile rises only to a height of this, determine the average force due to air resistance. Okay. So let me work this problem. Get my tablet here. Get my pen. Okay, let me get a page. Get a blank page. There we go. Okay, so let's see. This is Chapter 6. Let's see if we got some equations. The work done by a non-conservative force is the change in kinetic energy plus a change in gravitational potential energy. And the formula for kinetic energy is 1/2 mv squared. And the formula for gravitational potential energy is mgy. Okay, those are the equations I'm going to use. So the mass is 0.635. The initial speed is 15 meters per second. So how high would it go if there were no air resistance? Well, we need because we have these changes in things, what we need to do these problems and use this equation is an initial point, and a final point. So I'm going to take the initial point as when it gets shot up, And I'm going to take the final point when it reaches its highest point. Of course, the tablet's sitting on my lap. I'm sure if you have a pencil and paper, you can do a little better. So this is initial, I. This is final, F. If there's no air resistance, then this work done by the non-conservative forces on the left-hand side is 0. The final kinetic energy is equal to 0. The initial kinetic energy is 1/2 times the mass, 0.635, times, I'm not going to put units in here because it gets too long, times the velocity squared. We have everything in MKS units. And then the final gravitational potential energy is mgy, 0.635. It's a mass. G is 9.8. Our good old friend, 9.8. And y is the maximum height. That's the final potential energy. The initial potential energy is 0. So I'm going to call this mgh instead of y. All right, so I just got a little number crunching to do here. I'm going to move this to the other side of the equation. That's the initial kinetic energy, 1/2 mv squared, 0.635 times 15 squared. And over on this side, I got mgy, which is 0.635 times 9.8 times h. Got to do a little algebra. Well, this 0.635 cancels. 15 squared is 225. This is a plus now that I moved it over here. 15 squared is 225. 225 divided by 2 is, I don't know. And then I got to divide by 9.8. So h would equal 225, 15 squared, divided by 2, and then also divided by 9.8. So let me grab my contraption here. I don't have anybody to do arithmetic for me. So I'm going to take 225 divided by 2 equals that, and then I'm going to divide by 9.8. And I get 11.5. That would be meters. Get rid of my contraption here. Oops. So I just type in here 11.5. Easy enough. And I type in here, where are my units? There it is, meters. Good. Okay. Part B. Suppose the projectile only rises to a maximum height of 9.74. Determine the magnitude of the average force due to air resistance. Okay, so now the work done by the non-conservative force is not going to be 0. Work done by the non-conservative force, air resistance, is going to be the final kinetic energy minus the initial kinetic energy, 1/2 times 0.635 times v squared, 15 squared, plus the change in gravitational potential energy. Well, the final gravitational potential energy is going to be 0.635 times 9.8, but it doesn't go to 11.5 meters. It goes to 9.74 meters. So the work done by this non-conservative force, which is, by the way, always negative, at least in this chapter, I guess it could be positive if the non-conservative force was somebody pushing on the device. So I'd take that back. Anyway, this is just a little number crunching. I'm going to get, well, I know what I get here. No, I don't. I get a negative 1/2 times 0.635 times 15 squared. So that's 1/2 is 0.5 times 0.635. Is that right? 635 times 15 squared. I get a negative 71.43, 71.44 minus 71.44 joules would be, because this is energy, and plus 0.635 times 9.8 times 9.74. 60.61. Well, when I combine those two, I'm going to get a negative number. Anything like friction, air resistance, drag, those things all do negative work because they're always opposite the direction of the motion. So if I subtract 71.44, I'll get the work done is negative 10.83, negative 10.83 joules. But now they're asking me not for the work, they're asking me for the force. Well, I need a little more room. Here we go. Okay, I need another equation. I need that the work done by the non-conservative force is equal to a negative because it's in the opposite direction of the displacement. The force times the distance. Well, the distance is 9.74 meters. So if I take this, I get negative 10.83. And that's equal to negative F times 9.74. It looks like my force is going to be 10.83 over 9.74. Grab my contraption here again. So 10.83 divided by 9.74. 1.11 newtons. So let's see if that satisfies the Wiley plus gods. 1.11 and newtons. Where is newtons? There it is. Submit those answers. Yay, see, this green is really nice. Green is good. All right. Let's look at this last problem here. A helicopter starting from rest accelerates straight up from the roof of the hospital. The lifting force does work in raising the helicopter. So here's a non-conservative force that's doing positive work. An 810 helicopter rises from rest to a speed of that in a time of 4.5 seconds. During this time, it climbs to a height of 7.3 meters. What's the average power generated by the lift force? Okay. I need a little more room. I can erase some of this maybe. Here's my eraser. There it is. So let's erase this. I'm going to use the same equation. Namely right there. There's the equation I want. Oops, I need those equations too, but I can remember. Okay, the work done by the helicopter is what? It's equal to the change in kinetic energy. Well, initially, what's the helicopter doing? Initially, it rises from rest. So initially, it's got a speed of 0, and it's got a height, y, of 0. Finally, what's the helicopter doing? Well, it's got a speed of 11 meters per second, and it's got a height of 7.3 meters. So the work that this engine had to do to get it up there, it's got an 810 kilogram mass. The final kinetic energy is 1/2 times 810 kilograms times the final velocity squared, which is 11 meters per second squared, minus the initial kinetic energy, which is zilcho, plus the final gravitational potential energy, which is 810 grams times 9.8 times, how high is it at the end? 7.3 meters, minus the initial gravitational potential energy, which is 0. So basically, you see, this helicopter motor had to provide enough energy to give it the kinetic energy and also give it the potential energy that it's going to get. Okay, so this is a little bit of number crunching here. So the work done by the non-conservative force, the motor in this case, let me grab my calculator. So I'm going to take 1/2, that's 0.5, times 810 times 11 squared minus, plus, minus 0, of course, but I'm not going to, back that up, plus 810 times 9.8 times 7.3. And I get 106,952. That would have to be joules in the MKS system. Okay, but what's the average power? Well, we have to look back to last class. The definition of power is work divided by time. Might symbolize it like that. So how much time did it take? 4.5 seconds. So I would have to take 106,952 and divide it, joules, and divide it by 4.5 seconds. A joule per second, you'll remember from last class, is called a watt. Okay, oops, don't touch your face. So I'm just going to take that and divide it by 4.5. And I get 23767. That's a powerful motor. Watts. That's for large powers like this, that's 23.77, rounding to 2 decimals, kilowatts. A kilowatt is 1,000 watts. So let's see what units they got available here. They got watts. They don't have kilowatts. So I'm going to have to put in 23.77. Nope. 23,767. 23,767. And watts. Let's see if question attempts. You have 3 attempts on these questions. If you use up 2 of your attempts, a lot of times students keep doing the same thing over and over, entering the same number because they're sure they're right or they found an answer on the internet. A lot of these problems can be found on the internet, and many of the solutions that you get are wrong. But anyway, that one's right. So you better get that done if you want to get any points for this. So let's go back to Blackboard here for a minute. Course content, online content. Here's where the lectures are posted. Here's class for Monday, March 30th. In order to maintain some kind of credible attendance for this class, I'm going to give a little attendance quiz after each class. You can take it 3 times. There's 4 questions. They're just questions about what was discussed in class. And so that shouldn't be too bad. Anyway. Chapter 7. Okay, as I mentioned in class, probably, in discussion of in Chapter 6, you know, the work kinetic energy theorem just comes from Newton's second law mathematically. It's just a different way of looking at Newton's second law. Well, there's about 5, as I probably have mentioned, there's about 5 different ways to mathematically look at Newton's second law. And we're going to talk about 3 of them this semester. We've already talked about 2. Number 1 was F equals ma. That's kind of the starting most basic statement of Newton's second law. That's not how Newton stated the law, by the way. And then there's the work kinetic energy theorem, which was being guessed at by Leibniz in Germany. Leibniz and Newton had quite a controversy going on about who discovered what. They both claimed to be the discoverers of calculus. We don't want to get into that. Chapter 7 talks about Newton's second law from the point of view that Newton used when he stated it. This is just a pretty common example. Back when we had professional sports, you'll remember there was a game called baseball. The season was supposed to have started by now, and it hasn't. At any rate, the ball comes in, and the bat is moving towards the ball. So the ball has some speed coming in, about 90 miles an hour, depending on the pitcher. And then the bat comes in contact with the ball and exerts a force on it. And that force accelerates the ball and actually turns it around. That's a big acceleration. When you turn something around, that's a large acceleration. And the force depends on time. This is the collision time right here. This is the time that my cat Woody. This is the time that the ball and bat are in contact. And the force starts out little, it rises to some maximum amount, and then it falls down. And this is the average force right here, this horizontal line here. And it turns out that this average force has the same area underneath it as the area inside this curve. That's what they mean by the average force. Okay, so we're going to define 2 new terms. Impulse. The impulse, and the symbol for this is uniformly J, and it's a vector, is equal to the area under remember the work was the area under the force distance graph. This is the force time graph. It's the area under the force versus time graph. Well, this is a rectangle right here. And that's just F times delta T. The height of this rectangle is F, and the width of this rectangle is delta T. So it's just the average force. I'll just call that F right now. The average force times the time that it's acting. So it's force times time. And that's what we call an impulse. What units does it have? Well, we have units for force and time already. It's called the units are newtons times seconds. A newton times a second, a newton times a meter was a joule, remember that? Well, a newton times a second doesn't have a special name. It's just a newton times a second. So this name is open if you want to name this unit after yourself. Definition of linear momentum. That's something that an object has. This is something that happens to an object. An impulse is applied to an object. But this property of objects is called momentum. And the universal symbol for momentum is not m. You can imagine, can't use that. M is already very much used. The universal symbol for momentum, and it is a vector, is p. And it's equal to the mass times the velocity. Or in symbols, mv. In symbols that we're already using. So this is the big momentum. It's a common word in sports. But it's mass times velocity for us. And the units are simple. They're going to be just our units of mass, which is kilograms, times our units for velocity, which is meters per second. This Newton second, well, that's the same as a kilogram meter per second squared times seconds. See how one of these seconds cancel? And so the units of impulse are also Newton seconds, but they're also kilograms meters per second. Oh, look, the units for momentum are kilogram meters per second. So we have these two new physical quantities. And here's Newton's second law. Newton wrote his entire work in Latin. So here's law number 2. That's Latin for law number 2. And mutationem modus proportionalium sav. I actually took Latin. I'm so old that I actually took Latin in high school. But I can't read any of this. Anyway, what Newton, remember we said F equals ma was Newton's second law. As I have pointed out in the past, this is not the way Newton stated the law. This is the way that physics teachers seem to think it's the easiest to explain. What Newton referred to as a force, we now call an impulse, J. So when Newton used the Latin word for force, he was really talking about an impulse. And and Newton also talked about quantity of motion, which is the mass times the velocity. So what we now call momentum, Newton originally referred to in Latin as quantity of motion. Like a certain thing has a certain amount of motion. Its mass times its velocity. That's how much motion it has. We describe that, we use the word momentum for that. And so F equals ma, F equals m times a, remember, is the change in velocity over the change in time. So if I bring this delta t over to the other side, on the left-hand side I get force times delta t equals m times v final minus m times v initial, because the change in velocity is the final velocity minus the initial velocity. So F equals ma is mathematically the same as saying that the impulse that's applied to an object is equal to the change in momentum of the object. And that's the way Newton has described the second law here. And it turns out that this is quite a use when combined with Newton's third law for two objects colliding with one another, we'll see that we can arrive at a new principle. But anyway, that's enough for today, I think. I don't know how long I've been going on, but stay safe and stay home.